Welcome back, everyone, to the deep dive. As we browse the web, stream movies, and just do all the things we do online, we rarely stop to think about the invisible infrastructure that makes it all possible. But today, we're going to delve into a piece of that infrastructure, a technology that's absolutely crucial to how the internet functions, especially given the sheer number of devices that are now connected. We're talking about network address translation, or NAT.
NAT, the quiet workhorse of the internet. I mean, think about it. Every device on the internet needs a unique IP address, right? But the number of public IP addresses available is actually quite limited, especially with the older IPv4 standard. So how do we manage to connect billions of devices worldwide with this limited pool of addresses? Well, NAT's a big part of the answer.
Okay, so it's about stretching those IP addresses as far as possible. I get that. But I think a lot of people, even those who've heard the term NAT, might not really grasp how it actually works under the hood. What's the magic behind it?
Not so much magic as clever engineering. In essence, NAT allows a bunch of devices on a private network, like your home or office network, to share a much smaller number of public IP addresses, very often just a single one. So your home router, for example, will typically have one public IP address assigned by your ISP, and all the devices in your home, your phones, laptops, smart TVs, all share that one address when they talk to the outside world.
So it's like having a single phone number for a whole household, but each person has their own extension.
That's a pretty good analogy. And just like with phone extensions, NAT uses port numbers to keep track of which device on the private network is sending or receiving which data. But before we delve into the mechanics of that, let's step back and look at where NAT came from. Initially, it wasn't actually designed to address the IP address shortage.
Oh, really? What was its original purpose then?
Well, early on, one of the problems NAT aimed to solve was the hassle of readdressing entire networks when they moved physically or changed ISPs. Imagine having to manually reconfigure the IP address of every single computer and device, a real headache. NAT provided a way to avoid that by translating those internal addresses on the fly.
Makes sense. It's a lot easier to change an address at a central point than on dozens of devices.
Precisely. But then, as the internet exploded in popularity, and with it the number of devices wanting to connect, the issue of IPv4 address exhaustion became a looming crisis. IPv4 only allows for about 4.3 billion unique addresses. Now that sounds like a lot, but with billions of people and their increasingly internet-connected gadgets, smartphones, tablets, even refrigerators these days, it became clear that we were going to run out of addresses. Fast.
So net, originally intended as a convenience, suddenly became an absolute necessity to keep the internet growing.
You got it. And this is where the concept of IP masquerading, which is often used interchangeably with NAT, became crucial. It's essentially like giving a large group of people a single disguise to go out in public. The private network, with its own set of internal addresses that aren't directly visible on the public internet, gets masked behind a single public IP address.
Ah, so my home network is like a masked ball. Everyone inside has their own identity, but to the outside world, they all appear to be coming from the same place.
Exactly. Now, to make this masquerading act truly effective, another innovation came along in 1996, Port Address Translation, or PAT. This took the idea of address translation a step further by incorporating port numbers. You see, every communication on the internet, whether it's web browsing, email, or video streaming, uses specific port numbers. What PAT does is essentially create unique combinations of the public IP address and different port numbers for each device on the private network.
So it's like having multiple doors on that single public address, and each device uses a different door to send and receive its data.
Precisely. That's why PAT is often called Network Address and Port Translation, or NAPT. It allows many devices to share that single public IP address, all while keeping their internet traffic separate and organized.
That's brilliant, a real lifesaver for the internet as it continued to grow exponentially.
It's this deep understanding of fundamental networking principles, including the intricacies of NAT and PAT, that has been crucial for us at Stonefly as well. We've been at the forefront of SAN technology storage area networks for over 2 decades. Our expertise in networking and data storage goes hand in hand, especially in today's world where data is constantly flowing across networks. And being able to effectively navigate the complexities introduced by NAT, particularly in enterprise environments, is essential. If you're curious to learn more about how our solutions incorporate these principles and how we've been solving complex data challenges for over 20 years, visit stonefly.com or reach out to us at sales@stonefly.com.
All right, let's get into the nitty-gritty of how NAT actually works. We've got the big picture, but now let's zoom in on the mechanisms. To start, we have the simplest form of NAT called basic or one-to-one NAT. How does this one work?
Basic NAT is quite straightforward. It's a direct, one-to-one translation between internal private IP addresses and external public IP addresses. So if you have, say, 5 devices on your private network, you would need 5 public IP addresses. Each internal address gets mapped to a specific public address, and that mapping remains static.
So unlike the crowded masquerading ball we talked about, this is more like a one-on-one escort service. Each internal device has its own dedicated public representative.
Yeah, I like that. You could think of it that way. It's less about conserving addresses and more about connecting networks that might have incompatible address ranges. For instance, if 2 companies with different internal numbering schemes merge, basic NAT can help bridge the gap, allowing devices on both networks to communicate without a complete overhaul of their addressing.
So it's like a diplomatic protocol ensuring smooth communication between different addressing cultures. But if it's not primarily for address conservation, what actually gets modified during this translation process?
Well, in this basic form, the changes are pretty minimal. The NAT device, which could be your router or a specialized firewall, primarily swaps out the source IP address of the outgoing packet with the mapped public IP address. Of course, to ensure data integrity, the IP header checksum, which is like a fingerprint verifying the packet's content, needs to be recalculated to reflect the new IP address.
Right, we wouldn't want the packet to get rejected just because its fingerprint doesn't match.
Exactly. And any higher-level checksums, say in the TCP or UDP header, that happen to include the IP address also need to be updated. But in basic NAT, it's really just about changing those addresses.
Okay, so that's the one-to-one, but the real heavy lifting, the type of NAT that's most prevalent, is the one-to-many NAT, right? We touched on it earlier. It goes by a few different names: NAT, PAT, IP masquerading.
You got it. One-to-many NAT, or NAPT, often just called PAT, is indeed the workhorse of the Internet. And yes, it's also accurately described as IP masquerading because it allows a whole bunch of devices, each with its own private IP address, to share a single public IP address for communication with the outside world. It's how most home networks and many small businesses connect to the Internet.
So let's walk through how this actually plays out. Let's say I'm at home, browsing the web on my laptop. What happens to the data packets as they go from my laptop through my router and out onto the Internet?
Okay, so your laptop, along with all the other devices on your home Wi-Fi network, has been assigned a private IP address by your router. These are special ranges of IP addresses that, by design, are not directly routable on the public Internet. It's like having an internal postal code that only works within your neighborhood.
Okay, so my laptop has its local address. What next?
Now, when you type in a website address in your browser and hit enter, your laptop creates a packet of data that needs to be sent to that website server, which will be out there on the Internet somewhere, with its own public IP address. But your laptop's packet initially has your laptop's private IP address as the source address.
Right, because that's its identity on the home network.
Exactly. Now, this is where your router, which is acting as the NAT device, steps in. As that packet from your laptop tries to leave the home network and head out onto the Internet, the router intercepts it. The router knows that this private IP address can't be used directly on the Internet, so it replaces your laptop's private IP address with its own public IP address, the one assigned by your ISP.
Ah, so it's putting on that disguise, stepping in as the public face of my laptop.
Precisely. But here's the clever part. To keep track of which device on the internal network sent that packet and where the returning traffic should be delivered, the NAT device also makes note of the port numbers involved.
Oh, right, those doors we talked about?
Exactly. It records your laptop's private IP address, the port number that your web browser is using on your laptop, which will likely be a random high-numbered port, and it might also modify this port number to a different one as the traffic goes out, all while using the router's public IP address.
So it's like saying, okay, traffic coming back from that website on this specific public IP address and this specific port should be delivered to this specific device on the private network using this original port. It's quite a meticulous record-keeping system.
It has to be. Now, when the website server sends the web page data back to your router, because remember, it sees the traffic is coming from the router's public IP address, and the translated port number, the NAT device springs into action again.
It checks its logbook, right?
Exactly. It looks up that incoming port number in its translation table and says, ah, I know this one. This traffic belongs to that laptop over there. And then it reverses the translation process, replacing the destination IP address and port in the incoming packet with your laptop's private IP address and the original port number that your web browser is using.
So the web page data arrives at my laptop, none the wiser that it's been through this whole address juggling act.
It's quite seamless, isn't it? And crucially, this entire process allows many devices on your private network to communicate with many different servers on the Internet simultaneously, all appearing to be coming from that single public IP address thanks to the magic of port numbers.
It really highlights how crucial port numbers are to this whole operation. Without that extra layer of differentiation, the NAT device would be completely lost, wouldn't it?
Absolutely. It wouldn't know which device to send which data to. Everything would get mixed up. That's why it's called network address and port translation. And, as a company that's been deeply entrenched in the world of data storage and networking for over 2 decades, we at Stonefly have a profound appreciation for these intricate mechanisms that make modern internet communication possible. We've seen firsthand how NAT has shaped network architectures and how important it is to develop solutions that work seamlessly within these environments. If you're interested in exploring the kind of technology that addresses these complexities head-on, visit stonefly.com to see how Stonefly, a pioneer in FAN technology, can help.
Now, you mentioned earlier that communication usually have to be initiated from the inside, from the private network. Does this mean someone out there on the internet can't just decide to start sending data to my laptop directly?
That's generally the case. Because the NAT device only creates those translation entries when a connection is initiated from the inside, unsolicited incoming traffic from the internet usually gets blocked. Think of it as a built-in security feature. The NAT device acts like a bouncer in a club, only letting in those who have been invited or have previously made contact.
So it helps prevent random strangers from just barging into my network.
Exactly. Now, of course, there are ways to selectively allow certain types of incoming traffic if you need to, techniques like port forwarding, which we might touch upon later. But the default behavior of most NATs is to drop any incoming traffic that doesn't have a corresponding entry in its translation table.
So there's a balance between accessibility and security, and NAT leans towards security by default.
Right, and this is just one of the many nuances of NAT that anyone working with networks, especially those designing or implementing network-based solutions, needs to be very aware of. Stonefly, with our over 2 decades of experience in the field, has encountered just about every conceivable scenario involving NAT, and that expertise is baked into our solutions. We understand the importance of robust security and reliable connectivity, and that deep understanding guides everything we do. Stonefly is the pioneer of SAN technology. You can find out more about our approach at stonefly.com.
So we've talked about the basic mechanisms of NAT, both the one-to-one and the far more common one-to-many NAT. But I've also come across some talk about different types of NAT, which I gather refers to subtle variations in how different manufacturers implement NAT. How significant are these differences, and why should the average user care about them?
It's a great question. You see, while the core principles of NAT are fairly consistent, there can be subtle differences in how different NAT devices handle the translation of addresses and ports, and also in how they filter incoming connections. These variations can actually have a significant impact on the behavior of certain applications, especially those that rely on establishing direct communication between users who might be behind different NATs.
Oh, so things like online gaming, video conferencing, or peer-to-peer file sharing, where you want to connect directly to another user rather than going through a central server.
Precisely. For these types of applications, it's often necessary for them to be able to figure out their own public IP address and port number as seen by the outside world, and also to understand the type of NAT they're behind. Because different types of NAT can have different rules about what incoming connections they allow, this can create compatibility issues.
So it's like different dynwidths of the same language, the core concepts are the same, but the specific grammar can create confusion.
That's a great way to put it. And that's where this classification of NAT types, even though the original way of categorizing them has been superseded by newer standards, still provides a helpful framework for understanding the range of behaviors you might encounter out in the wild. It's less about memorizing the specific names and more about grasping that NATs don't all handle connections in exactly the same way.
Okay, so let's break down these different types. We often hear terms like full cone NAT, restricted cone NAT, and symmetric NAT. What's the gist of each of these?
Let's start with the most permissive one, full cone NAT. With a full cone NAT, once a device on your internal network, let's say your computer using a particular private IP address and port number, establishes an outbound connection to some server on the internet, the NAT creates a mapping to a specific public IP address and port number. And the key here is that after this mapping is created, any other host on the internet, regardless of its own IP address or port, can send packets back to your computer by using that mapped external address and port.
So it's like leaving the door wide open after you've stepped out.
Pretty much. Now, an address-restricted cone NAT is a bit more cautious. It's similar to full cone in that once your internal device makes that initial outgoing connection, it gets mapped to a specific external IP address and port. But the difference is that for an external host to be able to send traffic back to your device must have previously sent a packet to that specific external IP address.
Ah, so it's like you have to have exchanged contact information first before they're allowed to call you.
Exactly. And it doesn't matter which port the external host is using, the restriction is purely based on their IP address. Now, a port-restricted cone NAT takes this a step further, says not only do you have to have initiated contact with that external IP address, but they also have to be sending the reply from the exact same port number that you originally sent traffic to.
Wow, so it's very specific. And what about symmetric NAT? I've heard that one can cause quite a few headaches.
Symmetric NAT is definitely the trickiest one to work with, especially for certain applications. What it does is for every new connection that your internal device initiates to a different external host, even if it's using the same internal IP address and port, the NAT will assign a completely different external IP address and port mapping.
So it's not just about my internal setup. The external server I'm talking to also influences the mapping.
Exactly. And to add to the complexity with symmetric NAT, only the specific external host that received a packet from your device on that particular mapping is allowed to send packets back using that specific external IP address and port combination.
That sounds like it could create a lot of confusion, especially for things like peer-to-peer applications where you might be connecting to multiple different peers simultaneously.
Absolutely. And to complicate matters further, many NAT devices out in the real world don't neatly fit into one of these four categories. They might exhibit behaviors that are a mix of different types.
Now, we also mentioned RFC 4787 earlier. What is that, and how does it try to make sense of this whole NAT landscape?
RFC 4787, which stands for Request for Comments, is essentially a document that aims to standardize how we describe and categorize different NAT behaviors. It recognizes that there could be ambiguity in how terms like full cone or restricted cone are used, and it tries to bring some clarity by making a clear distinction between what it calls NAT mapping and NAT filtering.
Okay, so what's the difference?
NAT mapping refers specifically to the translation process, how the internal IP address and port are mapped to an external IP address and port for outgoing traffic. NAT filtering, on the other hand, is about the rules that the NAT device uses to decide which incoming packets from the external network are allowed to reach the internal network.
So mapping is how my traffic gets out, and filtering is about what gets let back in.
That's the gist of it. The RFC then goes on to define different types of mapping and different types of filtering. For mapping, it talks about endpoint-independent mapping, where the mapping doesn't change based on which external server you're communicating with. Address-dependent mapping, where the mapping can change based on the IP address of the external server. And address and port-dependent mapping, where both the IP address and port of the external server can influence the mapping.
And what about filtering?
Similarly, for filtering, there's endpoint-independent filtering, which is the most open, allowing any external host to send traffic back as long as they know the mapped public IP address and port. Address-dependent filtering, which only allows traffic from external hosts that you've previously communicated with. And address and port-dependent filtering, which requires both the IP address and the source port of the incoming traffic to match a previous outgoing connection.
It sounds like this RFC is trying to create a more precise language for talking about NAT behavior.
Exactly. The goal is to improve interoperability and to make it easier to design applications and network devices that can work reliably across different types of NATs. Of course, the real world is always messier than any standard can fully capture, and there are definitely NAT implementations out there that don't strictly adhere to these RFC guidelines.
So it's a step towards greater clarity, but there's always going to be some level of variation and unpredictability.
That's the nature of technology, isn't it? It's constantly evolving. And that's precisely why companies like Stonefly, who have been deeply involved in providing robust and reliable networking solutions for over 2 decades, are so valuable. We have a deep understanding of these complexities, and we design our offerings with a keen awareness of the diverse NAT behaviors that exist out in the real world. Our goal is to ensure seamless and secure data communication for our customers, regardless of their specific network environment. You can explore how we achieve that at stonefly.com.
Now, we talked earlier about how NAT, by default, makes it tricky for external hosts to initiate connections to devices on private networks. But for applications like online gaming or video conferencing, being able to establish those direct connections can be essential. How do they manage to overcome this inherent limitation of NAT?
Yes, the challenge of NAT traversal. It's a hurdle that many peer-to-peer applications have had to overcome. One relatively simple solution is port forwarding. This involves manually configuring your NAT router to say, hey, any traffic that comes in on this specific public port, forward it to this particular device on my internal network on this specific internal port.
So it's like creating a dedicated tunnel through the NAT.
You could think of it that way, and for some applications that's enough, but the downside is that it requires manual configuration on both sides, and it's not very dynamic or scalable, especially if you're dealing with constantly changing IP addresses or if you want to connect to many different peers.
And then we have more sophisticated techniques like the TCP hole punching you mentioned earlier.
Ah, yes, TCP hole punching. That's where things get really clever. The idea is to exploit the way many NATs handle outgoing connections to essentially trick them into letting inbound traffic through. And a crucial concept here is port preservation.
Port preservation.
It means that when your internal device initiates an outgoing TCP connection to some server on the internet using a specific source port number, the NAT device uses that same port number on its public IP address when it sends the traffic out to the internet. It's like keeping the label on the package consistent throughout the journey.
And why is that so important for TCP hole punching?
Because in TCP, which is the protocol that governs most reliable internet communication, each port on a device can typically only have one active connection associated with it at a time. Now, imagine two users behind different NATs who want to establish a direct TCP connection with each other. Let's say they're both playing an online game. They each initiate an outgoing TCP connection to a well-known public server. This could be a game server or some other rendezvous point. This server helps them exchange information about their external IP addresses and the port numbers that their NATs have assigned to them.
So they use this public server as a meeting point to get each other's contact details.
Precisely. Now here's the clever bit. They both simultaneously try to initiate a TCP connection to each other's external IP address and port number. Now, if their respective NATs have been kind enough to preserve the source ports they initially used for their outgoing connections to the rendezvous server, and if the timing of these simultaneous connection attempts is just right, something interesting can happen.
The NATs get confused.
You could say that. Because each NAT sees an incoming connection attempt on the very same port that it's currently using for an outgoing connection, it can sometimes be tricked into thinking that this incoming traffic is actually part of that existing outgoing connection. It's like two people trying to squeeze through a doorway at the same time from opposite sides. If they both push hard enough, they might just make it through.
So it's a bit of a hack, but a clever one if it works.
It is. Now, of course, this isn't foolproof. It relies on several factors aligning just right, and it's more likely to work with certain types of NATs than others.
So port preservation is crucial for TCP hole punching. How does UDP, the other main internet protocol, handle this?
UDP is a bit more flexible. Because UDP doesn't have the same one-to-one relationship between ports and connections, a single UDP port on a device can be used to communicate with multiple different endpoints, and it's also more common for applications to reuse the same source UDP port for different communications. So for UDP-based NAT traversal, predicting the external port number is generally easier, and port preservation isn't as critical.
So TCP is stricter about its ports, while UDP is more laid back.
That's a good way to think about it, but it's also worth pointing out that even beyond enabling techniques like TCP hole punching, port preservation in general can make things simpler for peer-to-peer protocols. If a NAT consistently preserves the source port, it means the application logic doesn't have to be as complex. It can potentially reduce latency because there's less need to rely on third-party servers to help discover the externally mapped port.
It's like having a reliable postal service that always uses the same return address, so you don't have to constantly check where your mail is coming from.
Exactly. Now, of course, there can be edge cases where port preservation might cause issues. For example, if two different devices on the same internal network try to initiate connections to the same external host using the same source port number at roughly the same time, the NAT might get confused. It might be forced to use a different external IP address if it has one available, or it might have to abandon port preservation for one of those connections to avoid ambiguity.
It's fascinating how these seemingly minor technical details can have such significant implications for how applications actually work.
Absolutely. And the widespread adoption of NAT globally really highlights the importance of understanding these mechanisms for anyone involved in networking or application development. Estimates from years ago suggest that a vast majority of Internet users were behind NAT devices. For companies like Stonefly, who have been immersed in these networking challenges for over 2 decades, it's been crucial to design our solutions with a deep awareness of these nuances. Our goal is to ensure seamless and reliable operation for our customers, no matter what type of NAT they might be behind. We know that connectivity is king, and our understanding of the intricacies of NAT is a key part of how we deliver that. To learn more about how Stonefly addresses these and other complex data challenges, visit stonefly.com.
So far, our discussion has focused on the big picture of NAT and the concepts of mapping and filtering, but let's zoom in even further and look at the individual components of a data packet and how they get transformed during the translation process.
Okay, so at the heart of Internet communication, we have these things called packets. Each packet is essentially a little bundle of data that's being sent from one device to another. Now, within each packet, you have several layers of information.
It's like an envelope with different sections for the address, the sender, the recipient, and the actual message.
That's a great analogy. So at the very basic level, you have the IP header. This is like the main address label on the envelope. It contains the source IP address, which is where the packet is coming from, and the destination IP address, which is where it's going.
Yeah, that's where NAT does its address swapping.
Right. But within the IP packet, you also have data from higher-level protocols like TCP or UDP. These protocols are responsible for managing the actual flow of data between applications.
TCP is like a reliable courier service that ensures the package arrives intact, while UDP is more like sending a postcard. It's faster but less guaranteed.
You got it. Now, within the TCP or UDP headers, you have source and destination port numbers. These are like those specific doors we talked about, allowing different applications on the same device to communicate with different applications on other devices without getting their data mixed up. And the combination of the IP address, the protocol, TCP or UDP, and the port number is what uniquely identifies a specific communication channel, often called a socket.
Okay, so NAT primarily focuses on the IP address and the port number. Does it look at the actual data within the packet?
Generally, no. NAT in its most basic form is just about changing addresses and ports to allow devices on private networks to communicate with the outside world. It doesn't usually care about the actual data being sent, which is often encrypted anyway.
Makes sense. So let's recap the whole translation process for a packet as it goes from my internal network out to the internet and then back again.
All right, so when your internal device, say your laptop, sends a packet, the NAT device, which could be your router, first checks the source IP address in the IP header. If it's a private IP address, and remember those are defined in a document called RFC 1918, it knows it needs to perform translation.
It pulls out its disguise kit.
Exactly. It replaces that private IP address with its own public IP address. If it's performing PAT, it also looks at the source port number and might choose to assign a new, unused port number. Critically, it records all of this in its translation table, the original internal IPN port and the new external IPN port. For any subsequent packets from that same internal source and going to the destination, it'll consistently use the same translation.
So the external server just sees a stream of packets coming from the router's public IP address.
Right. Now, when the server sends its reply back, say the web page you requested the NAT device intercepts the incoming packet, it looks at the destination port number and checks its translation table. If it finds a match, it knows where to send it. It reverses the translation, putting your laptop's private IP and original port number back into the packet header, and then forwards it to your laptop.
And if it doesn't find a match?
Then it typically drops the packet. Because it doesn't know which internal device the packet is intended for, it considers it unsolicited traffic and, for security reasons, simply discards it.
It's all about keeping that translation table up to date and accurate.
Precisely. And, this whole process, this constant manipulation of IP addresses and ports at a packet level, is something that we at Stonefly have been intimately familiar with for over 2 decades. As a company deeply rooted in data storage and networking, we understand the absolute criticality of these mechanisms for reliable data communication. We've spent years honing our expertise in these low-level details, ensuring that our solutions work seamlessly and efficiently within a NAT-filled world. If you want to explore how our experience and understanding of these fundamental technologies translates into robust, high-performance, and solutions, head over to stonefly.com.
So we've covered the core use case of NAT, which is allowing multiple devices on a private network to share a public IP address. Are there any other notable applications where NAT comes into play?
Yes, definitely. NAT can also be used in routing, specifically to address situations where you have overlapping IP addresses. This can happen, for instance, when 2 companies with separate networks, each using the same private IP address range, merge or need to be connected. Without NAT, you'd have chaos, because devices on both networks would have the same local address, leading to confusion about where traffic should go.
So it's like trying to merge 2 towns that both have a main street and a First Avenue. You need some way to disambiguate.
Exactly. NAT can act as that disambiguator, translating the addresses of one network as they communicate with the other, essentially creating separate addressing spaces and allowing them to coexist peacefully.
It's like having different area codes for those towns. What's the other application you mentioned?
Another important use case is in load balancing for client-server applications. Imagine you have a very popular website that gets a ton of traffic. Instead of having a single server handle all the requests, which could easily get overwhelmed, you might have a cluster of multiple servers working together, all providing the same service. NAT can be used to present a single public IP address to the outside world, representing this entire cluster of servers. Then the NAT device can distribute incoming requests across these different servers based on various algorithms, making sure no single server gets overloaded.
So it's like having a team of receptionists answering calls, making sure the workload is shared evenly.
That's a good way to put it. And this kind of load balancing can significantly improve the performance, reliability, and scalability of online services.
Now, we've talked a lot about the benefits of NAT, but it's not all sunshine and roses, is it? NAT has its drawbacks too, right?
Of course, no technology is perfect, and NAT, while incredibly useful, does introduce some limitations and complexities that we need to be aware of. One fundamental issue is that devices behind NAT don't have true end-to-end connectivity with the public internet. They can't always seamlessly participate in all internet protocols. Services that require incoming TCP connections that are initiated from the outside world can be tricky to set up.
We touched on this earlier. It's because the NAT device doesn't know where to send that incoming traffic unless there's a pre-existing outgoing connection.
Right, and this can also be a problem for certain protocols that rely on stateless communication, like some implementations of UDP. These protocols don't establish the same kind of persistent connections as TCP, so the NAT device might not have the necessary information to forward the incoming traffic correctly.
Right. So even though UDP is often used for things like streaming video and online gaming, where those direct connections are important, it doesn't necessarily play well with all types of NATs.
Exactly. There are ways to work around these issues, such as manually configuring port forwarding on the NAT device or using specialized techniques, but it adds complexity.
Now, earlier we discussed those application-level gateways, or ALGs. How do those fit into this picture of working around NAT limitations?
Right. ALGs are specifically designed to address a particular category of problems that arise with NAT. Some application layer protocols like active mode FTP